Thank you very much. Today I would like to tell you about quantum dot-based sources of non-classical light, and I would specifically focus on telecom wavelengths, and the motivation is quantum cryptography applications. So starting from the beginning, I would like to shortly motivate why we are interested in telecommunication spectral range and why quantum emitters can be important for quantum cryptography and communication. And then I will go to quantum dots, which in my case will be epitaxially grown semiconductor quantum dots. I will say why we should or shouldn't use them as quantum emitters. I will give examples of performance at 1.55 micrometers, and then I will shortly compare them to other quantum emitters. So coming to telecom spectral range, this is the optical loss in a standard silica fiber, and what you can see is that the global minimum of this loss is at 1.55 micrometers. So from now on, this is my region of interest. This is because it will be compatible with existing fiber infrastructure. Also, to be fully compatible, you need fiber sources, not only sources emitting at the right wavelength. But typically, if you want the highest performance for the quantum channel, you will probably need dark fibers anyway. And this allows for long distance data transmission. And if we want to work in this spectral range, we have two options. Either we choose quantum dot, which emits directly at 1550 nanometers, or we choose something that emits at lower wavelength and you use frequency down conversion to actually change it to 1550, and I will show examples of both. So when it comes to semiconductor material systems good for this purpose, we have the following options. You can see the energy gap versus lattice constant, and here is the target wavelength. So what we have here is either indium arsenide on gallium arsenide, indium arsenide on indium phosphide, or we can also have mixture of the antimonide materials. These are our options because we don't want to have too large lattice mismatch, because then the material is strongly strained. Plus, it will not allow to grow large quantum dots needed for long wavelength fabrication. This is already the case for gallium arsenide based structures because the lattice mismatch is on the level of 7% to the substrate. And this is already too much. So they need some strain engineered strategies to actually reach the target wavelength. For the indium phosphide base and gallium arsenide, this can, let's say, naturally emit in this spectral range. The second thing you need to consider is the refractive index, high refractive index contrast materials that will be lattice matched to your emitter, so you can create photonic structures, because as I will show later, you need some photonic environment engineering to optimize performance of your source. And then you need to think about the growth method that will allow to reach high crystal quality, and typically strain-free and high symmetry nanostructures are better for most of the applications. And just very shortly to name the cryptography or communication elements that needs non-classical light sources. So there are many quantum key distribution protocols, and one of them, BB84, needs single photons to be performed. Then, if you have source of entangled photons, then you can use different protocols like Eckert. And then you also have already one of the building blocks of quantum repeater, because you need in at least one of the implementations source of pairs of entangled photons that you can send to distant locations. And the measurement you have to perform is actually two photon interference, which means you need to have identical photons from two remote sources to realize that. And of course, for quantum teleportation, there is a similar requirement that you need pair of entangled photons to transfer the state of the original particle to the state of another one at a distant location. And these are all building blocks of quantum networks, and this is the long-term motivation behind this work. And now, first, I will start with advantages of quantum dots. So they have discrete energy levels, which means that at certain conditions, either by growth or by excitation scheme, you can choose a two-level system which will inherently emit single photons, which means you have something with the right statistics already. In contrast to weak coherent pulses, where you take a Poissonian source and you try to diminish its power to the level where you have single photons, but this has inherent errors because you cannot get rid of the multi-photon emission events. And it was shown that this gives you such a pure single photon statistics, give you some advantage in the case of lossy channels in terms of the length of transmission. So they can be triggered, again, in contrast to probabilistic sources based on nonlinear processes. So we can really have photons on demand. And then they are compatible with well-developed semiconductor technology, which means we can think about such a sophisticated integrated photonic circuits, and it should not be that difficult to scale it up to larger chips. And the advantage is that they are quite flexible. In a sense, you have engineering opportunities on the level of growth of these structures. Plus, you can have post-growth tuning with external magnetic, electric, or strain field. You can fine-tune the properties of your quantum dot after all. And then for the quantum dots emitting at shorter wavelengths, it has already been shown that these are nearly ideal single photon sources. And the plan now is basically to transfer this into the different material systems, so the quantum dots emitting at longer wavelength. So there should be no fundamental reason why not. They are the best in terms of single photon purity, evaluated as a correlation, second order correlation function at the zero time delay. So the probability of multi-photon event is on the level of 10 to minus 4. This is at telecom wavelengths. At shorter, it can be one order of magnitude better. And then it was shown already for quantum dots at the second telecom window, so 1.3 micrometer, that you can have electrical driving, but the downside is that you have incoherent excitation in that way, and a lot of best performances are reached under coherent excitation, and that you can really have fiber sources, so you can optimize the position of the fiber to a single quantum dot, create rigid connection, and have like a plug and play device in which in the telecom fiber you have single photons, right? These are the advantages, but there are also disadvantages of this approach. So first of all, there are a lot of engineering possibilities, but unfortunately there are no two identical quantum dots, right? So if you don't do any tuning post growth, you basically have very low chance of finding something that will overlap spectrally, right? So this is difficult in case of quantum dots. So you actually need this extra tuning knob to be able to have two identical sources. And you have to do it locally if you think about scalability. This is doable, but let's say something to remember. Then, because it's a quantum dot in a semiconductor matrix, it means it interacts with the environment strongly. So we have other carriers in the environment, which leads to spectral diffusion. And we have, of course, phonons, and this is what's limiting the coherence of the state you create. Also, if you think about semiconductor material with refractive index on the order of 3, the total internal reflection will actually not let the photons out so easily, only at a very narrow range of angles. And this means that you need this engineering of photonic environment to get more light out. Otherwise, it will be single percentage of the photons you will actually collect from what the dot is emitting. So you need to do something to overcome this. And the issue is that those quantum dots which emit at telecom wavelengths do not emit at room temperature. And now I will go through the free material systems I told you about and show you some examples of how they are performing nowadays. So the idea is to take the known system, gallium arsenide based, and to use some strained engineering. The strained engineering is to put a metamorphic buffer layer with a composition gradient, which is in between the substrate and the quantum dot, to hope that all the defects at threading this location will actually at some point stop propagating, and that the virtual substrate for the quantum dot growth will be of high quality. You can see that the surface looks nasty, but it was good enough to grow quantum dots at 1550 and to have narrow single quantum dot lines. And what people did with it up till now is that they have single indistinguishable photons. So they actually put the quantum dot of this type in a circular Bragg grating cavity. They got the enhancement factor of a spontaneous emission of 4 and the G2 on a reasonable level. And what was at this time a record was 35% of the indistinguishability of single photons. And of course, if you filter spectrally, you can get higher visibility, but the issue is that you get the generation rate of your source lower because you are throwing away some photons. The brightness was already in the megahertz range, and the wavelength was Fourier limited. And then it was also shown that it's possible to strain engineer, to strain tune such a source just by putting a piezo material below the thinned sample and then applying a voltage. And then what we can see is that by applying the voltage, we can change the emission energy of the lines, and we can do it reversibly. But the tuning range is only 0.25 nanometers, so we already have to be quite close to the target wavelength, because you can either use it to be in resonance with some cavity or to produce two exactly the same sources. And then it was stable over time once you set the wavelength. And they also showed that the probability of multi-photon events is relatively low. Okay, and then we can also use quantum dots to generate polarization entangled photon pairs. We are using biexciton-exciton cascade for this. There are two bright excitonic states separated by the fine structure splitting, which is there because because we have exchange interaction and because the potential is never fully symmetric. And then we have one cascade and the other cascade, and the state that is emitted by such a free level system is actually entangled. And of course, you have to show that it's entangled in all three polarization bases to prove that you have quantum entanglement. In this case, the splitting was 5 micro EV. And this is the minimal amount of cross correlation measurement you have to do. So basically, what they show is that there is a correlation in all three polarization bases. And when they calculate the fidelity to one of the maximally entangled belt states, it was above half. So it's the proof of the entanglement. Of course, if you do more measurements or you try to use numerics, you can extract the two-photon density matrix. And if you do the fidelity measurement as a function of time, you can even see the oscillations, and the period of them is related to this fine structure splitting. It can be done better. So by using smart excitation scheme, here the two-photon excitation scheme was used to directly or resonantly excite the biexciton and then to observe the cascade. This is how it looks like with the laser that needs to be strongly suppressed in the spectrum. And in this case, the fidelity was over 95%. So this is, let's say, the state of the art for metamorphic buffer layer on gallium arsenide. And now we change the material system to indium phosphide based. And this is still the record for the purity of the single photon emission on the level of 10 to minus 4. Again, this time the spectrum looks like this, and it was resonantly excited into the first excited state. And the structure looks like this. There is the quantum dot, and there is so-called horn structure, and the light is, and the dot is excited, and the emission is collected from this side. And here you can see how the electromagnetic field looks like. And with these structures, it was shown that the extraction efficiency, so the percentage of photon that you collect, is in the range of 11%. And they demonstrated quantum key distribution of for 120 kilometers with 3 megahertz emission rate. And then this is actually our contribution to the field. So we have access first, thanks to our collaborators, to MOCVD grown indium arsenide indium phosphide quantum dots and MBE grown. And what I would like to show here is that thanks to the, again, circular Bragg grating cavity, the parcel factor is in the range of 5. The extraction efficiency was almost 17%. And the G2 is on the level of 10 to minus 3, so one order of magnitude worse than the record, but it can also be achieved under non-resonant excitation, which is much easier to realize and much more universal. The indistinguishability 35%, and the 7 micro EV is the fine structure splitting. As always, all the features, each of the features is in a different structure, and this is probably the main challenge now in this community. So the better results for the indistinguishability were achieved in this such a structure also in the circular Bragg grating cavity. You can here see the spectrum under phonon assisted pumping, and the quantum dot was positioned in the cavity in the deterministic fashion. And this is how the G2 looks like, with the central peak zoomed in here. And then the indistinguishability, here you have the reference measurement of distinguishable photon, and here for the indistinguishable photons. And this is over 91% without any post selection, right? So this is the raw value, but with this specific excitation scheme. Okay, and one maybe peculiar example is that actually using droplet epitaxy grown quantum dots of a high density, the Toshiba Cambridge group managed to have an quantum LED. So they have a lot of quantum dots here. They put an electrical contact, so they inject carriers electrically. This is how a spectrum looks like. And then what they manage is to get over 80% entanglement fidelity. And what's even more interesting, they manage to preserve it up till 90 Kelvin, that the state is still entangled. And the spectrum looks like this at this high temperature limit. Okay, and last material system I would like to shortly introduce, because there is still not much work on it, is antimonide based. And actually, because the lattice mismatch here is very low, the different method has to be used, and the method is used nanohole droplet etching. So there is a gallium droplet imposed on the barrier material, and in the presence of the antimony flux, the antimony is sucked to the droplet, and actually the gallium antimonide material is then going outside because of the kinetics of the process, and we have a nanohole which is further filled in with the quantum dot material. And the material is interesting because of the high refractive index contrast materials, and because it can be directly grown on silicon. If we want to put together optics and electronics, this is a good thing for us. Okay, this is how the surface of such a sample looks like. This is the AFM scan of the etched nanohole in 2 perpendicular directions. So you can also see it's quite symmetric. This is a single quantum dot spectrum, and this is the G2 measurement taken from this particular line, and we have 5% probability of multiphoton events in this case. And what is even more important, just by changing the indium composition, we can reach the target wavelength. And what you can see here is not so typical for quantum dots, that the broadening of the whole ensemble of quantum dots is below 10 millieV. It basically means that we have much higher probability to have similar quantum dots in this case than in the other growth methods and material systems. And this is a single quantum dot measurement with very well separated single quantum dot line at the target wavelength. And then the option, if you don't want to develop new emitters emitting at 1550. You can use old emitters and then try to do difference frequency generation. And this is typically done to get to 1550. So you have your quantum dot at a shorter wavelength. This is a periodically polled lithium niobide waveguide, which is working as the nonlinear medium, and you need a seeding laser which wavelength need to fulfill the energy criteria or frequency criteria for the difference frequency generation, that at the output you have 1550. This is the goal. Of course, the first question is whether after such a process the quantum statistics is preserved, and it was shown yes. And you need, of course, a very low noise process. Disadvantage is that the brightness is limited by the end-to-end efficiency of this conversion process. And the advantage are that we have very good sources already at shorter wavelengths. And by tricks, I mean that you can tune them, that you can have charge control, and so on. And then, actually, if you have two remote quantum dots which are not the same, using two different lasers, you can actually erase the difference in wavelength. So you can, from non the same sources, get the same sources after the conversion process. And what has been done here, so the conversions are on the level of 35-40%, the efficiency. And this is the quantum dot before conversion, and this is the same quantum dot after conversion. And then you see that most of the things are similar. Of course, the problem is that the counts are lower after conversion, and the indistinguishability actually suffers the most because of the any fluctuations or time jitter in the laser itself. And then it was possible to do it a little bit better, but still we are on the level of 88% and 40% the efficiency. And I guess the nicest result for now is actually that two sources, remote ones, which were 300 kilometers apart, were interfere, right? This is measurement for single sources, and the interfering gave the interference visibility above 60% from two completely different sources far, far away apart. And if we use temporal filtering, we can even do better. It was also shown that the quantum teleportation can work. So we have one source which works as a single photon source, then it's converted to 1550, and the second source, a source of entangled photons. One of them is the one that we will measure as a reference, and the second one is going to be converted to 1550, and then we have the two photon interference experiment. They did it. Of course, it all depends how good are the initial photons, and the fidelity was over 70%. But of course, what is a problem is that the coincidences, the free photon coincidences, are in the millihertz range, right? So you can show it in the lab, but you don't want to wait for it. And the 70% is if you filter spectrally. So this is also why these free photon coincidences were so low. But it was used anyway to show a teleportation in the optical fiber loop in the city environment. And what they show is this is the time filtered, this is non-time filtered. And again, if you do not filter, then you can see that there is few percent loss in the fidelity. Otherwise, it behaves in the same manner. So coming to the comparison to different platforms, so any two-level system will do, but with quantum dots, the problem is that they work at cryogenic temperatures. This is the main drawback. You can, of course, have defects in different material systems, but then it's a little bit harder to do the engineering, but they will also do the job. And then we have nonlinear processes. And the issue here is that they are probabilistic. So they can work at room temperature 1550, but they are probabilistic with nature. But because of the fact that you don't need to cool them down, actually these and the weak coherent pulses were the main workhorse for the quantum cryptography. But the problem is that the state quality is coupled to generation rate. So if you want to have better G2, you need to sacrifice the generation rate to lower the probability of multi-photon events. And here the issue is that our state quality is linked to temperature and excitation scheme. Okay, just briefly, if we look for advantages, we have Fourier limited lines for the quantum dots, and we can have gigahertz or higher emission rates, but the problem is temperature. But if we compare to cold atom and ion, this might actually be advantage if we look here. But of course, the line width of atom is better, and we can have identical atoms easily. Okay, so the last point would be that we have the G2 values which are the lowest. And if we compare to other system at 1.5, we actually have millisecond lifetime, which means the generation rate will be very low. And then I would like to point out or sum up once again the performances. And from the list here, you will see that probably the most difficult challenge is to combine all in one structure. And with this, I thank you for your attention.
Thank you very much for this introduction in this quite different but fascinating and useful topic. Questions? There is one, yes.
Does it work? Oh, thanks for the very interesting talk. I was particularly interested about the results for remote interference with the two sources at 50-50 at 300 kilometers. So when you reach 90% HM or something, it's very impressive. So I was wondering what sources are you using for that?
So
what's the
the
fireback?
remote.
This one. Like, what sources is used there?
So gallium arsenide quantum dots. These are what are
With the conic, the conic design that you showed in the first slides.
no. The conical one was indium arsenide on the indium phosphide. This horn structure. So this was not in this case used. So this is gallium arsenide because this is the down converted source. So this is not directly emitting at 1550, but it's emitting at 940, and it's converted to telecom spectral range.
Okay, so you have a Bragg resonator before the down conversion, and then okay.
Yeah.
Thanks.
Thank you. We have time for more questions. I may have one for now. So your performance, especially in the G2, is overwhelming, I would say. But could you comment on the physical reasons for like the remaining two photon events?
Yeah, I know it should not be there, but it's there. Okay, so what we can have is actually the emission, so some background emission from the sample still. If you, for example, excite non-resonantly, you can still have some defects or anything.
So it's not necessarily from the dot itself, because I imagine there's one dot, right?
Yeah, there is one dot, but there is one dot, but there are many transitions in the dot.
I see.
Right? This is the issue. So first of all, there is the surrounding, and we filter spectrally. So if something has exactly the same emission wavelength, it will add up to our histogram. This is one thing. The second thing is that the dot has different transitions, which we of course try to filter spectrally.
I see.
And then there are actually, then you are going into such subtleties as dark counts of the detector and so on, right? Exactly. So then you are getting into the detection system non-idealicity.
I see. Yeah, thank you. Anything else?
1 more minute you have.
1 more minute, yes. Well, if not, I'm sure. Oh, yeah, there is one. Good.
Oh, no.
I also need to do some project on this generating cluster state and using quantum dot. So, but I was wondering, you mentioned that the frequency can be very, very different among one dot and the other. And is there really no way to control the generation frequency, or
So if you have a transition in a quantum dot and you want to control it, you have options like electric field, right? So you can put it in the diode structure, apply electric field, and then you can shift the resonance. Plus, you can, of course, then do control charging of the quantum dot. So you can also decide whether you want neutral complex, trion, and so on. So this is very useful. But at some point, you will actually be lowering the overlap between the electron and hole function, so the intensity of your transition will drop. So this has some limit, let's say this electric field tuning. And the second thing, of course, you can do temperature, but this will not work locally, and it also introduces more interaction with phonons and lower intensity. The best choice for now we have is a strain tuning, so with this piezo material. You can do it the way I showed, that you just take the piezo ceramic and you glue your sample on it. But the work of Armando Rastelli or Rinaldo Trotta, they show you can have this 6-leg structure that you can locally tune a single quantum dot in 3 different axes. And then you have the full control. So you can change the transition energy, you can change the fine structure splitting and the biexton binding energy independently. But of course, you can do it in a certain range, so the dot should be already as close to ideal dot that you want, because you will not tune it by 50 milli EV, right? Something more like a single milli EV level, you can do it.
Thank you very much.